Greetings and welcome. Today we're going to be looking at hyperbolas, which are a type of conic section, and they have the most in similar, I guess, with ellipses. But let's take a look at what's going on with hyperbolas. So they'll have two vertices. All right, so here's our vertices. A center. All right, so that's not that unexpected. So here's our center point. Try to make it look like a capital C. And the distance to those vertices will be A from C. Alright, so A and minus A units away. And the distance between the two vertices, or the line segment that connects them, is called the transverse axis. But we'll come back to that in just a moment. Let's see. Another significant point we have is B. Or a length is B and negative B, and those give me two other points, which are the endpoints of the, my mind just went blank on that one, conjugate axis. Conjugate meaning to pair, so it's the pair axis with the transverse, and these two things so far don't actually represent anything on the hyperbola other than the vertices. But I use them to construct this box, which is going to allow me to visualize the rest of the graph. So this box, I just want to point out, is 2a across and 2b in height. And b and a, there will be a relationship later on that we'll discuss between those and the foci, but the B is not necessarily shorter than A, where in the case of the ellipse it was. So that's one of the differences between vertices and ellipses. So let's see. So if I draw the line segments through the endpoints of this box, these are going to be two diagonal asymptotes in our hyperbola. Alright, so these are actually not part of the graph, but they will be used to create the graph. And the graph is going to exist, alright, from the foci, and it'll approach the asymptotes infinitely, but never reach them. So somewhat of a futile existence. And so our hyperbola, let's see if I can get a better curve there, something like that, is just going to be the yellow portion of this graph. Alright, and then the only other points I think I need to indicate here are the foci, which the foci are not within the vertices, they will be beyond the vertices, and are little c units away from the center. So little c. So center I try to indicate with a capital C, and it is an ordered pair. Little c is a single number. Alright, so these would be my foci. So there's my two foci. So I guess this would be negative c over here technically. And the foci are not on the graph, but they're used in constructing the graph. So the actual definition of a hyperbola is, I guess we can write it down real quick. So it is the set of all points, let's see, or the locus of all points is another way we could describe it, in the plane in which the difference, alright, so this is a key indicator separating it from the ellipse, in which the difference of the distances from two distinct boy. Yeah, it's throwing a bunch of vocab at us here, but that's okay. From two distinct fixed points Alright, and I'll actually indicate those as the foci. Alright, our blue points there is constant. Okay, so what that means, let's see if I can pick a good color for this. We'll do orange, that's good enough. So here's a point on my graph, and here's the distance to this foci, and here's the distance to this foci. Alright, so this longer distance subtracting the shorter distance is always the same, no matter what point we happen to be on the hyperbola. Alright, so if it was an ellipse, I would have said that the sum of the distances are constant. In this case, the difference of the distances is constant. And it doesn't matter which point that is. And I just want to point out that if that point was one of my vertices, alright, let's see, to the foci, this distance would be c minus a, alright, and this distance, is a, another a, and another c minus a. But, and if I subtract those, that ends up giving me just, oh, my mind just blanked out on that. Let's actually write that down. So let's see, it would have been 2a plus a c minus a. Oh, I think it's going to be 2a across. So 2a plus a c minus a is this little distance right here. Subtracting this distance over here, which is another c minus a, yeah, is equal to 2a. So that constant distance is actually going to equal 2a in this case. So that's the formal definition of a hyperbola. We're not necessarily going to use that directly too much. We're going to kind of be more aware of these individual locations and being able to draw the graph based off of the asymptotes, which tends to be the easier approach. So let's see. And then as far as the relationship between A, B, and C, for hyperbolas, the following is true. A squared plus B squared is equal to C squared. Alright? Which in the case of an ellipse, for an ellipse, this was A squared minus B squared equals C squared. For a hyperbola, it's the sum. And part of that reason is that C squared is going to actually be bigger than A and B. So C is bigger than A, where within an ellipse, C was the shorter distance of the two, right? C would have been somewhere within the value of A for an ellipse, right? So these are true for hyperbola. And then just a side note, I guess, is for ellipse. We had that a squared minus b squared equals c squared, and c was less than a, were facts regarding ellipses, just so we're aware of that. So let's do an example so we can jump into this. Oh, actually, I got to write an equation. So once again, there's actually going to be two types. Let's see, maybe I'll write it this way. Equation. We'll do graph, and then facts, I guess. So we can kind of represent this. So there's going to be two separate cases. So one is going to be for the horizontal ellipse, or sorry, hyperbola, which is essentially what I had drawn here. Horizontally orientated, meaning it's opening away from itself in a horizontal direction, or the transverse axis is horizontal. I guess let me actually throw that into. Yeah, so transverse axis, which by the way happens to have a length of 2a, and the conjugate axis, which is 2b in length. All right. So let's see. So our graph here would be this one, where it's horizontally oriented, right? Something like that. Our equation will be similar to ones we've experienced before, most similar to the ellipse, I suppose. So it'll be x minus h all squared all over a squared minus y minus k all squared all over b squared equals 1. So the only difference between this and an ellipse is this is now a minus sign. All right, and that kind of makes sense because difference was the only difference in the definition of this as well. So let's write down some facts about this. So it's horizontally oriented. The center is going to be at h comma k. We've seen that before. Let's see, we can find A, B, and C. Let's do the vertices. So in this case, because it's horizontally oriented, I'm going to add and subtract the values of A from the center, at least the horizontal coordinate of the center, right? So H plus or minus A, comma K, all right, because it's horizontally oriented, all right? And then I guess I could call them the endpoints of the conjugate axis. If I had to try to come up with an abbreviation, I would add and subtract the values of B to the y coordinate. All right, and I just want to once again clarify that the endpoints of the conjugate axis are not actually part of the graph. The graph of the curve itself is only this yellow portion here. All right, so those are those. The foci are always going to be along the same axis as the major axis, or transverse axis, sorry, in this case. So that would be h plus or minus c, comma, k. And then, yeah, I guess I'll do equation of transverse. All right, in this case is going to be horizontal, right? The transverse is going to pass through the vertices and the foci. So it's horizontal in this case, so it's going to be y equals k in this case, right? Which is the y coordinate of both of those points. Maybe in the next video I'll end up talking about the equations of the asymptotes, but for now I don't think we need to worry about that. Alright, and let's see. So for the equation of a vertically oriented hyperbola, it's going to look very similar. Oh. Except this time, a squared is underneath my y term, and b squared is underneath my x term. Now, back in the days of ellipses, I told us that we could determine which orientation the ellipse was, basically saying that the larger denominator will be under the orientation, right? So And that's kind of true in this case as well, in the sense that this minus sign I could think of as being applied to the b squared. So even if the magnitude or the absolute value of b is bigger than the absolute value of a, if it's negative, we'd think of it as a smaller number. All right. Where in this case, the minus sign would be applying to this as well, whichever the smaller denominator is. And the smaller denominator would be under my x term, so this would be vertical, because the larger of the two, the non-negative, the positive one, will be under the y. So I base this more off of which, so I guess I'll write this, to determine orientation. The positive fraction, I guess, yeah, use the positive fraction. Okay, so it's not just based off of whichever denominator looks bigger. So that right there is the place for common mistake. And then, so yeah, so vertically oriented hyperbola would look something like this. All right, la la and la la, and it's symmetric horizontally speaking and vertically speaking. There's even, I guess, some rotational symmetry there if we wanted to think of it that way. But yeah, so that's what we'd end up having. And most of these facts, I think, can be easily derived. I don't recommend memorizing all these. The way I think of these is I think of the picture where A and B and C would bring me, and I develop those from there. So the center is h comma k again, and I just want to point out that k will always be with the y, so don't just think that k is the second numerator's number there, so don't let that throw you off. Let's see, the vertices, in this case vertically oriented, so I'm going to add and subtract a to my y coordinate of the center because it's vertical. Y coordinate is the vertical component of that center, right? So let's see, equation of conjugate axis, or endpoints of conjugate axis, I think is what I have that representing, would be h plus or minus b comma k. The foci would be h comma k plus or minus c. So once again, the foci exist on the same axis as the vertices do. And let's see, and then equation of transverse would be x equals h, because it's the x coordinate is the only thing that'll be the same for all of these points, and the transverse axis will pass always between your vertices, your foci, and I guess technically your center. So those are kind of all of our facts about the equations of ellipses. And let's see, this video is going very long. I think I'll do the next example in another video. So this is, I guess, an introduction to hyperbolas. So thanks for watching.